It was promised to be the engineering marvel of the century, a bullet train rocketing from San Francisco to LA in under 3 hours. The California High-Speed Rail Authority designed a system to span over 800 miles, connecting the state's economic powerhouses.
Voters approved the dream in 2008, envisioning speeds of 220 miles per hour, rivaling the fastest trains in Europe and Asia.
Phase 1 was designed to cut through the Central Valley, the agricultural heart of the state, before tackling the mountains.
But turning blueprints into steel and concrete became a battle against costs, politics, and the sheer scale of the land.
The reality began here, not in the cities, but in the Central Valley, chosen as the testing ground for American high-speed rail.
Construction officially kicked off in 2015, breaking ground on a project that would soon face unprecedented hurdles. Before a single rail could be laid, hundreds of miles of land had to be acquired, cleared, and prepped.
Every inch of the 776-mile planned system required precise topographical mapping to ensure safety at top speeds.
The route sliced through existing farms, requiring delicate negotiations and massive earthworks.
By 2025, the budget had swelled, with nearly $14 billion spent just to get the initial segments off the ground. The estimated cost for the full Phase 1 build-out skyrocketed to over $128 billion, threatening the project's future.
Despite the political storms and federal funding withdrawals, the men on the ground kept working.
The ultimate goal is crossing these mountains to reach Los Angeles, an engineering feat that remains years away.
Delays pushed the completion date further back, with an interim goal now set for 2038 to connect the Bay Area to the valley. The first step of physical construction is grading, creating a perfectly flat surface for the high-speed tracks.
High-speed trains cannot tolerate steep inclines, so the earth must be moved to meet strict geometric standards.
Soil compaction is critical. If the ground shifts beneath the tracks, a train moving at 200 miles per hour faces disaster.
The hidden enemy of the schedule was utility relocation, moving thousands of miles of cables and pipes.
Before the rail line could advance, existing water and power infrastructure had to be dug up and rerouted.
Moving high-voltage transmission lines required coordinating with utility companies, causing months of delays.
Old roads and abandoned structures in the right-of-way had to be demolished and cleared out.
Millions of cubic yards of earth and debris were hauled away to clear the path for the future alignment. Engineers drilled hundreds of feet down to ensure the soil could support the massive weight of concrete viaducts. In the Central Valley, the soil composition varies, requiring custom foundation solutions for every mile. Environmental regulations required strict dust control during the massive earth-moving operations. Once the utilities were moved and the ground leveled, the corridor began to look like a transportation spine. Precision is key. The alignment must be accurate to within millimeters over hundreds of miles. With the ground prepped, the materials began to arrive: concrete, steel, and American manpower. The preparation phase alone took years, a testament to the complexity of building in modern California.
To cross roads and rivers, the train must be elevated on viaducts, starting with deep foundation piles.
Steel rebar cages, some over 100 feet long, are lowered into the ground to reinforce the concrete piles.
Liquid concrete is pumped deep into the earth, anchoring the structure against earthquakes and heavy loads.
Above the piles, workers construct the footings, massive blocks of steel and concrete that support the columns. Thousands of steel ties are done by hand, a grueling process essential for the structural integrity. Carpenters build wooden molds around the rebar to shape the vertical columns. The columns rise from the fields, poured in stages to ensure the concrete cures properly.
Vibrators are used to settle the concrete, ensuring a smooth finish and solid core free of air pockets.
Once cured, the forms are stripped away, revealing the gray pillars that will hold the high-speed line. These columns, known as piers, now dot the landscape of the Central Valley, waiting for the trackway.
In seismic zones, these columns are thicker and reinforced with extra steel to withstand ground shaking.
Quality control is rigorous. Any crack or imperfection means the work must be repaired or redone. Specialized heavy equipment is brought in to handle the next phase, the superstructure.
Digital modeling guides the physical work, ensuring that what is built matches the complex engineering designs.
Attention to detail is paramount, even on the parts of the structure that will be buried underground.
Crossing the San Joaquin River required a massive pergola structure to protect the ecosystem below. While concrete is common, steel girders are used for longer spans where extra strength is needed. Precision lifting places these multi-ton beams onto the pier caps with only inches of tolerance. Ironworkers bolt the beams into place, working hundreds of feet in the air. The skeleton of the high-speed rail was rising, a new monument in the American West. The deck where the trains will run is heavily reinforced to prevent flexing under high-speed loads. To speed up construction, segments of the bridge deck are precast nearby and lifted into place. This method matches the speed of assembly lines, treating the bridge like a giant Lego set. Industrial-strength epoxy seals the segments together, making them act as a single continuous beam. Post-tensioning cables are threaded through the concrete and pulled tight to squeeze the segments together. This tension gives the bridge incredible strength, allowing it to span long distances without sagging.
The Cedar Viaduct is a prime example of the complex grade separations needed to cross existing highways.
Once the skeleton is complete, the final deck is poured, creating the flat surface for the tracks. Laser-guided machines ensure the deck is perfectly level, a requirement for 220 mph travel. The concrete is treated to prevent cracking as it dries under the harsh California sun. Mile by mile, the disconnected segments began to link up, forming a continuous aerial highway. From the ground, the scale is immense, designed to last for over a century of heavy use.
Safety barriers are installed to protect maintenance workers and contain the train in case of derailment.
Expansion joints allow the massive concrete structure to expand and contract with the heat without breaking. Proper drainage systems are integrated to keep water off the tracks during the rainy season. The viaducts minimize the impact on farmers, allowing tractors and crops to pass freely underneath. Aesthetic finishes are applied to the concrete to blend the modern structure with the local environment.
As the sun sets, the magnitude of the engineering effort becomes clear, a bridge to the future.
As the heavy work moves forward, crews restore the land below to its original state.
The train won't always be in the air. It transitions smoothly from viaducts to raised earthen embankments.
Where the train stays on the ground, roads must be moved over or under the tracks to prevent collisions.
Dozens of new overpasses are built to carry local traffic safely over the high-speed line.
These grade separations are crucial for safety, eliminating the dangerous level crossings found on older railways. Retaining walls are built to hold back the earth and protect the rail corridor in tight urban areas. Alongside the physical track,
A digital network is laid to control signals and communications. Heavy crash walls are erected to separate the high-speed trains from parallel freight lines.
One by one, the intersections of the Central Valley are transformed, separating cars from the future trains.
In Fresno, the line dives into a massive trench to pass under the city streets without disturbing traffic.
Concrete is sprayed onto the walls to stabilize the soil, a technique known as shotcrete.
The finish must be smooth to ensure the structural concrete poured later bonds correctly. The floor of the trench is reinforced to handle the immense weight of the passing trains.
Day and night, concrete trucks poured the foundation of this subterranean highway.
This trench allows the high-speed rail to pierce the heart of the city without dividing the community. Security is paramount. High fences ensure no unauthorized access to the high-speed corridor.
With the path ready, the track system begins. It starts with ballast, crushed stones that lock the tracks in place.
Specialized trains distribute the ballast evenly along the track bed.
Tamping machines pack the stones tightly, ensuring the track won't shift under vibration. Unlike wood, high-speed rail uses heavy concrete ties to maintain precise gauge and stability.
These components are manufactured domestically, supporting American industry. The steel rails are delivered in quarter-mile lengths to minimize the number of welds needed.
Flash butt welding fuses the rails into one continuous ribbon of steel, eliminating the click-clack of old trains.
Every weld is ground and inspected ultrasonically to ensure it is as strong as the rail itself.
Automated machines clip the rail to the ties with consistent pressure, securing the line. To power the electric trains, thousands of steel poles are erected to hold the overhead wires. Miles of copper contact wire are strung under high tension to provide a steady stream of 25,000 volts. Tensioning systems keep the wire flat regardless of temperature changes, ensuring constant contact with the train. Traction power substations are built at intervals to convert grid power for the high-speed system.
A sophisticated positive train control system is installed to monitor speed and prevent collisions automatically.
The physical infrastructure is now a continuous line of steel, ready for the first wheels to roll.
Stations are more than stops. They are multimodal hubs being built to revitalize downtown areas.
Massive canopies are erected to shade passengers from the Central Valley heat.
Modern glass and steel designs reflect the futuristic nature of the high-speed service.
Infrastructure for moving thousands of passengers an hour is installed, linking the platform to the street.
In the north, the Salesforce Transit Center awaits, the future terminus for the high-speed line. The vision is a seamless connection, moving passengers from San Francisco to Los Angeles in under 3 hours.
However, the daunting tunnels of Pacheco Pass still stand between the Central Valley and the Bay Area.
With costs for the full system estimated up to $128 billion, the path forward relies on future funding.
For now, the focus is the interim goal, connecting Gilroy to Bakersfield by 2038.
Before passengers can board, months of rigorous testing will verify the safety of the tracks and power systems.
Every vibration, every amp of power is recorded to certify the system for 220 mile-per-hour operations.
As speed increases, the engineering is pushed to the limit, proving the viability of the design.
It represents a leap forward, leaving the old diesel era behind for a clean, electric future.
The spine is built. The concrete and steel are real. The question remains, when will the full body be complete?
For the workers on the ground, the politics don't matter. They built what they were asked to build.
Thousands of American jobs were created, training a new generation in high-speed rail construction.
From the orchards of the valley to the tech hubs of the Bay, the physical link is slowly forging a new California. Supporters see a necessary evolution for a crowded state. Opponents see a cautionary tale of mega project management.
But the concrete stands, a permanent mark on the landscape, waiting for the high-speed future to arrive.
This is the story of the California High-Speed Rail, a monumental ambition built 1 yard at a time.